Hello everyone and welcome to Sally and Bytes. Today, I am here to teach Chapter 3, Computational Thinking, for the Class 11 students of Computer Science. In this video, we are going to discuss about Introduction to Problem Solving, steps for problem solving, algorithms, flowcharts, pseudocode and computational thinking. So let's dive in and get started. Computers have no intelligence or thinking power. Before solving a problem using a computer, we need to understand it. The user must have a clear understanding of the problem to instruct the computer correctly. Effective problem solving using a computer requires understanding of the problem and programming concepts. With proper instruction, computers can be powerful tools for solving complex problems. Before writing a program, it's important to analyze the problem and understand the solution. A program is a set of instructions to solve a problem using data processing. The process of writing a program is called programming. Writing correct instructions in proper sequence is important when programming. Precise step-by-step instructions should be inputted to the computer to solve the problem. Problem solving involves identifying a problem, developing an algorithm, and implementing the algorithm to develop a computer program. Many problems in our daily lives require problem solving. Problem solving involves defining a problem, determining its cause, and identifying, prioritizing, and selecting alternatives for a solution. Implementation of a solution is also part of problem solving. Examples of problems that require problem solving include developing a mark sheet or calculating simple interest. Writing clear and correct, step-by-step, instructions in proper sequence is important when programming. Problem solving involves identifying a problem, developing an algorithm, and implementing the algorithm to develop a computer program. Here are the steps for problem solving. Analyzing a problem, developing an algorithm, coding and testing and debugging. Let's see one by one in detail. The first step in problem solving is analyzing a problem. It's very important to understand a problem before finding a solution. We need to read and analyze the problem statement, which can help list the principal components of the problem and decide core functionalities. By analyzing a problem, we can figure out the inputs that our program should accept and outputs that it should produce. The second step in problem solving is developing an algorithm. A solution should be derived before writing program code for a problem. An algorithm is a set of sequential steps represented in natural language. An algorithm is like a well-written recipe for a dish. The tentative solution plan is done until we get the desired solution. More than one algorithm may be possible for a given problem, and the most suitable solution should be selected. The third step in problem solving is coding. After finalizing the algorithm, we need to convert the algorithm into a format, which can be understood by the computer to generate the desired solution. Different high-level programming languages can be used for writing a program, code. The instructions must be correct and given in the right sequence for the problem to be solved properly. It is important to record the details of the coding procedures followed and document the solution for later stage. The fourth step in problem solving is testing and debugging. Testing is an important step in software development. The program should be tested on various parameters to ensure that it meets user requirements and generates correct output for all possible inputs. Testing should include checking for correct output and response time. Standardized testing methods like unit testing, integration testing, system testing, and acceptance testing are followed in the software industry. Errors or defects found during testing are debugged or rectified and the program is retested. Maintenance of the solution involves fixing problems, answering user queries and serving requests for modification of features. Thus, problem-solving stages help develop computational thinking and offer accurate solutions to problems. In our day-to-day life, we perform activities by following a certain sequence of steps. For example, getting ready for school, preparing breakfast, driving a car, solving a puzzle. To complete each activity, we follow some steps. And that is algorithm. An algorithm is a set of step-by-step instructions for solving a problem or performing a task. While writing an algorithm, it is required to clearly identify the following: the input to be taken from the user, processing or computation to be performed to get the desired result, the output desired by the user. Here's an example of an algorithm to find the largest number in a list of numbers. Step 1. Start with the first number in the list and store it as the current largest number. Step 2. For each subsequent number in the list, compare it to the current largest number. Step 3. If the current number is greater than the current largest number, store it as the new current largest number. Step 4. Repeat step 2 and 3 for each remaining number in the list. Once all numbers in the list have been compared, the current largest number will be the largest number in the list. This algorithm can be implemented in any programming language, such as Python, Java, or C++. Here's a simple algorithm to find the greatest common divisor, GCD of two numbers. Step 1. Start with the two numbers you want to find the GCD for. In this case, 56 and 64. Step 2. Find the smaller of the two numbers. In this case, 56 is smaller. Step 3. Start a loop that will check all the numbers from the smaller number down to 1. Step 4. For each number in the loop, check if it divides both of the original numbers evenly. If it does, it is a common divisor. Step 5. Keep track of the largest common divisor found so far. Initially, this can be set to 1. Step 6. After the loop has finished, return the largest common divisor found. In this example, the algorithm finds that the GCD of 56 and 64 is 8. Hence, it is clear that we need to follow a sequence of steps to accomplish the task called algorithm. Why do we need an algorithm? Here are some of the reasons why algorithms are necessary. A programmer creates a program to instruct the computer to perform desired tasks. Before writing the code, the programmer needs to create a roadmap, or plan for the program, known as an algorithm. Algorithms are essential for clear visualization and problem solving. Algorithms are used for a wide range of tasks, including searching, messaging, document editing, online booking, banking, and gaming. Writing a correct algorithm is the first step to programming, and a correct algorithm leads to a reliable, accurate, and efficient solution. Algorithmic problem solving involves two phases: deriving an algorithm to solve the problem and converting the algorithm into code. Coding is comparatively easier since the logic is already present, and it is just a matter of adhering to the syntax rules of the programming language. Next, we will see the characteristics of a good algorithm. A good algorithm is one that solves the problem efficiently and effectively while adhering to certain characteristics. Here are some of the key characteristics of a good algorithm. First point: clear and unambiguous. A good algorithm should be clear and unambiguous, with well-defined steps that are easy to understand and interpret. Second point: well-defined inputs and outputs. A good algorithm should have well-defined inputs and outputs, and the inputs should be relevant to the problem being solved. Third point: correctness. A good algorithm should provide correct results for all valid inputs. Fourth point: efficiency. A good algorithm should be efficient, that is, it should require minimal time and resources to execute. Fifth point: scalability. A good algorithm should be scalable, that is, it should be able to handle large inputs without running out of memory or time. Sixth point: maintainability. A good algorithm should be easy to maintain and modify as needed. Seventh point. Generality. A good algorithm should be general enough to handle a wide range of inputs and solve a variety of related problems. Eighth point. Robustness. A good algorithm should be able to handle unexpected inputs and error conditions without crashing or producing invalid results. Ninth point. Traceability. A good algorithm should be traceable, that is, it should be possible to trace the execution of the algorithm and debug it if necessary. A flowchart is a visual representation of a process or algorithm that uses symbols to show the sequence of steps involved. Here are some symbols used in a flowchart. Ovals show a start point or end point in the code. Arrows show connection between different parts of the code. Rectangles show processes. For example, calculations. Parallelograms show inputs and outputs. Diamonds show a decision or condition. Example, if else, while and for. Let's see an example. Draw a flowchart to find average of 3 numbers. To solve this problem, we will ask the user to enter 3 values which get stored in 3 variables a, b, c respectively. We will then calculate the average of 3 variables and store it in a variable avg. Finally, we will print the value stored in the variable avg. Let's see another example. SpeedNet Limited plans to give a 7% year-end bonus to each of its employees earning rupees 20,000 or more per month and a fixed rupees 1,500 bonus to the remaining employees. Draw a flowchart for calculating the bonus for an employee. To solve this problem, we will ask the user to enter the salary of the employee, which gets stored in a variable, salary. We will then check the condition if salary greater than 20,000. If the condition is yes, we calculate the bonus as 7% of the salary and print the bonus amount. If the condition is no, we have fixed amount of rupees 1,500 is printed as bonus. Pseudocode is a high-level description of an algorithm or a program, expressed in a simple and informal language that is easy to understand. It is not an actual programming language, but rather a way to express the basic logic of a program before writing it in a specific programming language. A good pseudocode should not be in a specific coding language. It should draft the structure of your code. It should be understandable to humans. Let's see an example. Write a pseudocode that reads marks of 10 students and displays average of marks. Look at the pseudocode and follow me. At first, we set total to 0. Then set marks counter to 1. Now the condition starts here. While marks counter is less than or equal to 10, we have to input the next marks. Then, we add the marks into the total. Next, we have to set the average by dividing total by 10. Finally, display the average. Let's see another example. Write a pseudocode along with Python code to get a user's name as the input and then concatenate this name with hello message as hello, name. Pseudocode is a simple and informal way of writing programming code in English. There are no standard rules to write pseudocode. So we just get the username as input and display the output. But, in Python code, we follow some syntax or rules to get input and store in a variable and print the output. Next, we can discuss about computational thinking. Before computers can be used to solve a problem, the problem itself and the ways in which it could be resolved must be understood. Computational thinking techniques help with these tasks. Computational thinking allows us to take a complex problem, understand what the problem is and develop possible solutions. We can then present these solutions in a way that a computer, a human, or both, can understand. Computational thinking enables us to work out exactly what to tell the computer to do. The key components of computational thinking are decomposition, pattern recognition, abstraction, and algorithms. Let's see in detail, one by one. Before computers can solve a problem, the problem and the ways in which it can be resolved must be understood. Decomposition involves breaking down a complex problem or system into smaller parts that are more manageable and easier to understand. The smaller parts can then be examined and solved, or designed individually, as they are simpler to work with. Why is decomposition important? If a problem is not decomposed, it is much harder to solve. Dealing with many different stages all at once is much more difficult than breaking a problem down into a number of smaller problems and solving each one at a time. Breaking the problem down into smaller parts means that each smaller problem can be examined in more detail. Similarly, trying to understand how a complex system works is easier using decomposition. For example, understanding how a bicycle works is more straightforward if the whole bike is separated into smaller parts and each part is examined to see how it works in more detail. We do many tasks on a daily basis without even thinking about or decomposing them, such as brushing our teeth. Example 1. Brushing our teeth. To decompose the problem of how to brush our teeth, we would need to consider which toothbrush to use, how long to brush for, how hard to press on our teeth, what toothpaste to use. Example 2. Solving a crime. It is only normally when we are asked to do a new or more complex task that we start to think about it in detail, to decompose the task. Imagine that a crime has been committed. Solving a crime can be a very complex problem as there are many things to consider. For example, a police officer would need to know the answer to a series of smaller problems. What crime was committed? When the crime was committed? Where the crime was committed? What evidence there is? If there were any witnesses? If there have recently been any similar crimes? The complex problem of the committed crime has now been broken down into simpler problems that can be examined individually, in detail. Once we have decomposed a complex problem, it helps to examine the small problems for similarities or patterns. These patterns can help us to solve complex problems more efficiently. Pattern recognition involves finding the similarities or patterns among small, decomposed problems that can help us solve more complex problems more efficiently. What are patterns? Imagine that we want to draw a series of cats. All cats share common characteristics. Among other things, they all have eyes, tails, and fur. They also like to eat fish and make meowing sounds. Because we know that all cats have eyes, tails, and fur, we can make a good attempt at drawing a cat, simply by including these common characteristics. In computational thinking, these characteristics are known as patterns. Once we know how to describe one cat, we can describe others, simply by following this pattern. The only things that are different are the specifics. One cat may have green eyes, a long tail and black fur, another cat may have yellow eyes, a short tail and striped fur. Why do we need to look for patterns? If we want to draw a number of cats, finding a pattern to describe cats in general, for example, they all have eyes, tails, and fur, makes this task quicker and easier. We know that all cats follow this pattern, so we don't have to stop each time we start to draw a new cat to work this out. From the patterns we know cats follow, we can quickly draw several cats. We experience pattern recognition in everyday situations like drivers look for patterns in traffic to decide whether and when to switch lanes. People look for patterns in stock prices to decide when to buy or sell. Scientists look for patterns in data to derive theories and models. We look for patterns and learn from them to avoid repeating the same mistake. Once we have recognized patterns in our problems, we use abstraction to gather the general characteristics and to filter out of the details we do not need in order to solve our problem. Abstraction involves focusing on the essential features of a problem while ignoring irrelevant details. In order to draw a basic cat, we do need to know that it has a tail, fur, and eyes. These characteristics are relevant. We don't need to know what sound a cat makes or that it likes fish. These characteristics are irrelevant and can be filtered out. We do need to know that a cat has a tail, fur, and eyes, but we don't need to know what size and color these are. These specifics can be filtered out. From the general characteristics we have, tail, fur, eyes, we can build a basic idea of a cat, that is, what a cat basically looks like. Once we know what a cat looks like, we can describe how to draw a basic cat. Why is abstraction important? Abstraction allows us to create a general idea of what the problem is and how to solve it. The process instructs us to remove all specific detail and any patterns that will not help us solve our problem. This helps us form our idea of the problem. This idea is known as a model. If we don't remove, we may end up with the wrong solution to the problem we are trying to solve. With our cat example, if we didn't abstract, we might think that all cats have long tails and short fur. Having abstracted, we know that although cats have tails and fur, not all tails are long and not all fur is short. In this case, abstraction has helped us to form a clearer model of a cat. Before an algorithm can be designed, it is important to check that the problem is completely decomposed. An algorithm is a plan, a set of step-by-step instructions to solve a problem. If you can tie shoelaces, make a cup of tea, get dressed or prepare a meal, then you already know how to follow an algorithm. Algorithms can be represented in various ways, such as pseudocode, flowcharts, or programming code. Algorithms are used for many different things, including calculations, data processing, and automation. Thanks for watching. Watch the upcoming videos. Chapter 3. Getting started with Python, which includes Python programming language, downloading and installing Python, interacting with Python, Python IDLE, Python shell, command line interaction, Python editor window, working in script mode. You can check the link in the description box below.